Here I'm going to really hone in on the capillaries themselves. So my key takeaways for this little video are going to be for you to be able to describe some of the features in the vascular system that help these capillaries to play their role as exchange vessels. I want you to consider what is being exchanged, and then to be able to go on and explain how this exchange occurs. And so what are the competing forces that are at play on the arterial side of the capillary bed versus the venous or venule side of the capillary bed. What drives those forces and how do they help explain the pushing and pulling actions that we see in these capillary beds? So capillaries are oftentimes referred to as exchange vessels because this is not only the site of gas exchange, where you have oxygen that our heart has diligently worked to pump out, right? Where you have this oxygen making its way and being carried to the tissues that are not shown here. But you also have CO2 coming from the tissues that needs to be able to jump into these capillaries to be carried away. In addition, you're also going to have nutrients that are going to be exchanged here. You have waste products that are going to be jumping from the cells into the venous side of the capillaries. So there is quite a bit that is being exchanged here. And you have a capillary bed that is able to access just about every cell in the body. So not only is this figure oversimplified, but it is immensely oversimplified, right? You want to picture these capillary beds just about at every muscle, at every cell site of the body is where you want to picture these beds actually reaching. So they branch significantly, and we're going to see in future videos that we can also regulate the quantity of blood flowing through here by controlling these precapillary sphincters. We can either constrict and reduce the volume of blood going through, or we can relax those sphincters and allow more blood to reach these capillaries. It's a little bit more on their anatomy. So there's different types of capillaries out there. The rest of this video is really going to focus on what we call continuous capillaries. It's the most common, and with those, you're really going to see that they are composed of these, if you think back to the tunica intima, it's going to be comprised really just of those endothelial cells. And then you have a basement membrane that's not shown here. But there are little slits and pores between these that allow for fluid, that allow for water, that allow for gases to pass. You have what are called fenestrated capillaries. We're going to see those come up soon with the chapter on the kidneys, and we look at glomerular filtration. So those are going to allow additional things that are a little bit more porous. So you will see that a little bit more crosses. And then the most porous of the capillaries are called sinusoidal capillary in locations of the body like the liver, the spleen, bone marrow, places where you need to not only have cells leaving, but also proteins as well. One of the reasons that the capillaries are so good at being these exchange vessels is that our whole vascular system is designed to not only reduce pressure at these capillaries, which we have talked about already with those arterioles coming just prior to the capillaries. Those are the resistance vessels. We see pressure drop significantly to ensure that we don't have too much pressure going through these delicate capillary beds. But what I haven't yet talked about is this idea of cross-sectional area. And so the take-home point here is that blood flow is going to be inversely related to cross-sectional area, which means that as blood flow, as the speed, the velocity of blood flow increases, we're going to see that the total area is low. Another way to think about that is where the total cross-sectional area is high, like at the capillary beds, velocity is going to be low. So some analogies help immensely here. So this could represent something like the aorta. This could represent the vena cava, right? So aorta, vena cava, you have more arteries and they are smaller. You have even more arterioles and they're smaller still. And you have the most, out of all these vessels, you have the most capillaries, and they're the smallest of all. And so just running with this piece of things, you could think about the aorta as being a river. So the water is you've got a high volume of water, you have fewer rivers, and the water is going to move very rapidly. So the velocity is going to be at its highest at our rivers in the places where we have fewer vessels that are wider. On the other extreme of things, you have all the little creeks and tributaries that eventually make their way coming from these major rivers. So you have far, far more of these. And if you think about the speed of water moving in a river versus a small little brook, no doubt it's going to move much slower at this brook. Additionally, because you have so many creeks, right, we're going to see that the cross-sectional area is going to increase.
So to elaborate on the cross-sectional area of these regions, you really do want to think about the area. So if I were to take a graphic looking at the different vessels, to get at the cross-sectional area of the aorta or the vena cava, right, you would actually be upstream of here, but you'd be taking a cross-section here and taking a cut right here, and it would look like, let's say, this. And so we're saying, okay, it is all of this area. If you were to slice the aorta or to slice the superior and inferior vena cava, turn them on their side and literally measure the area. Whereas if you are to calculate or determine the cross-sectional area of the capillaries, imagine thousands and thousands of these capillary beds distributed all over your body. And even though they're quite tiny, if you start adding up all of these tiny little capillaries and their cross-sectional capacity and adding hundreds and thousands of these, you can see that it wouldn't take too long, and of course this isn't to scale, but it wouldn't take long at all to surpass the cross-sectional area that is given, or rather that is provided in the vessels like the aorta or the vena cavas. Just to conclude here, you can say that the flow of blood is inversely related to cross-sectional area. So in the aorta or vena cava, where the cross-sectional area is significantly smaller, blood flow is going to be higher. In places where the cross-sectional area is significantly larger, like the capillaries, where you have hundreds and thousands of these that all add up, that is going to slow down the flow of blood. And that makes a lot of sense because you want to slow the flow of blood to ensure that you have time to sufficiently exchange the nutrients. And that's where I want to head next, is looking at this idea of what does it mean to have capillary exchange? What is being exchanged and how does this exchange occur? Right? On the arterial side of things, we're going to see that we need to get stuff out of this side. And we'll look at what those sorts of things are. And that's going to have to actually pass through the interstitial fluid before it can then reach our tissues. On the reverse side, we have products, we have CO2, we have waste products coming from our tissues that have to go through this interstitial fluid and need to get back in to the venous side of things so that it can be carried away. So we essentially have pushing forces at play on the arterial end of the capillaries, and we have what we're going to term for now pulling forces on the venule side of these capillary beds. So in the pictures preceding, I have drawn the capillary as though it's a single vessel, but do appreciate that capillaries are present in beds, right, that branch extensively like what's shown here. So let's take a closer look. So here is my version of capillary exchange. So to orient you, we have the arterial end on this side on the left, and the venous end is going to be on this side to the right. So let's think about some of the things that are going to be leaving the blood and some things that are going to be entering the blood. So first and foremost, right, we've seen different types of gas exchange. When we covered the respiratory system, we talked about external respiration and internal respiration. And this is really the site of internal respiration. So you want to think about the oxygen that has to leave these vessels and enter into our interstitial fluid and ultimately make its way into the tissues. Okay, so that's one thing that's going to have to leave. In addition, you're going to have substances like amino acids leaving. So this is the nutrient piece of this. So amino acids need to leave the arterial end of things to eventually make their way into the tissues. Glucose, right? Sugars, nutrients are going to leave. On the pulling end of things, so on the venous end, we pull things back into the vessels. And so we're going to need to be able to reabsorb water. We know that CO2 is going to be produced by these cells, right? A component of cellular respiration. And that CO2 needs to be taken up into the venous end of things so it can be carried away and make its way to our lungs. So this is one of the things that's going to be pulled back in. I also should point out that water would also be present on this side, so you do have water leaving. Now, significantly, what's not leaving at these capillary sites, so what I've drawn here, these are supposed to be our red blood cells. And then in orange, I've drawn what we are going to call plasma proteins. And so if you look at the concentration of plasma proteins on the arterial end versus the venous end, you'll see that it doesn't change. So we don't have plasma proteins that are leaving the capillary in large forces. So we're going to see that the plasma proteins remain quite consistent, moving from the arterial end of things to the venous end of things. We've seen some plasma proteins before. Notably, one that we've covered is albumin. And we covered albumin in that blood chapter, and I noted at the time that it's one that's going to come up because it plays a significant role in creating osmotic pressures. So at this point, I've talked about some of the various substances, gases that are either leaving the blood on the arterial end or returning to the blood on the venous end, being pulled back into it. This green dotted line is totally imaginary, just trying to draw a distinction between the arterial end and the venous end. So moving on to more closely look at what are the factors that push and what are the factors that pull. So I'm going to use some abbreviations here. So osmotic pressure, I'm going to use OP. And then hydrostatic pressure, I'm going to use the abbreviation HP. Hydrostatic pressure, you can really think about as being almost identical to blood pressure. And so what is the source of pressure in our vessels, right? Coming from the left end here, first, the main thing that should come to mind is our heart, right? The heart is the source of these hydrostatic pressures on the arterial end of things. And so what we're going to find is that there are significantly higher hydrostatic pressures on the arterial end of things. And those forces become significantly smaller on the venous end of things. A lot of that pressure is lost with regard to this exchange, right? We've lost some of those, we've lost a little bit of water, we are further away from the heart, so pressure deteriorates in that regard. Now, what doesn't change are what we are going to call, again, these osmotic pressures. And the plasma proteins are the source of these pressures. And so if you think about osmosis, right, that is water moving across a membrane to create equilibrium. And if you have all of these plasma proteins concentrated inside of these vessels, but you have few, if any, plasma proteins that leave these vessels and enter the interstitial space, and imagine again all this water out here in these interstitial fluids, right? Well, what you're going to see is that the water is going to be drawn in. These plasma proteins create osmotic forces, create this pulling pressure that allows for fluids to return into the venous end of things. So whereas hydrostatic pressure significantly decreases going from the arterial end of things to the venous end of things, you actually don't see that osmotic pressure changes. It's going to be consistent on the arterial side versus the venous side. And to put a number around this, these are some pretty small values, but around 25 millimeters of mercury would be a pretty typical osmotic pressure. So running with that value would be about 25 here and 25 here. And again, the units are millimeters of mercury, or mmHg. And so it's not that osmotic pressure changes because these plasma proteins are consistent from one side to the next. It's just that hydrostatic pressure, the pushing forces that move stuff out of these capillaries, decrease so much going from the arterial side to the venous side of the capillary. And so what you're ultimately doing is you're looking at how much pushing pressure do we have versus how much pulling pressure. And so the question really becomes, what is the net pressure difference on these two sides? So on the arterial side, hydrostatic pressures went up. And then on the venous side of things, it's getting a bit messy over here, but you have the osmotic pressures that are going to dominate over the pushing hydrostatic pressures. So again, it comes down to what is the net force acting on these vessels? Is it predominantly our osmotic pulling forces or our hydrostatic pushing pressures coming from the heart?